Hi, I'm Kelly Providence, trainer for Solargen, and today in this video we're going to show you how to calculate the coldest day voltage and the hottest day voltage for your PV module and PV strings. First thing, we need to find our module data. This is a SolarWorld SW275 watt module. So we look at the standard test condition VOC of 39.4 and the VMP of 31. So these are the two voltages that we're going to change. This one we're going to change for the coldest day and this one for the hottest day. We need to also look at the temperature coefficient for each one of these. For VOC, we have a temperature coefficient of 0.31% per degree C, or K. And for max power, we have a temperature coefficient of 0.41% per degree C, or K. So this is the amount that's of voltage that's actually going to change per degree centigrade, different from standard test condition. Let's take a look at our formulas and start working this problem. This is the coldest day temperature calculation for voltage. Voltage is going to rise proportionate to the number of degrees colder than 25 degrees C that we're going to experience on the coldest day of the year. Now, it's important to understand that when the coldest temperature and voltage occurs. This is early in the morning when the PV array first wakes up, when the inverter or the equipment sees the voltage because the sun is just not coming up, but the sun is not directly on the PV array, which means that the cell temperature, the module temperature, is exactly the same as the ambient temperature outside. So whatever that temperature is, that is the same temperature we're calculating at the module. Hottest day calculations are not the same. This occurs during the middle of the day, and cell temperature is actually hotter than ambient temperature. So let's take a look at this formula. This is the number of degrees different from standard test condition 25 degrees C multiplied by the temperature coefficient. So this gets our multiplying factor for us. Let's look at this equation worked out. We're going to do this, of course. I've had this data input for us down below, and I have the temperatures from ASHRAE for Atlanta, Georgia. It shows the dry bulb mean temperature, coldest temperature, is minus 10 degrees C, and the dry bulb mean max temperature is 37 degrees C. So this is not the extreme coldest and hottest temperature on record, but the mean temperature, the dry bulb mean. That's what we want to use. Here you can see we've plugged the numbers in. We have minus 10 is 35 degrees lower than 25 degrees C, the standard test condition. So this is our multiplier. This is how many degrees multiplied by the temperature coefficient we're looking at to give us our multiplier. And our multiplier is 0.1085. These multiplied together give us this factor here. And we add 1 to it to include the voltage itself, and we have 1.1085 times 39.4 volts gives us a new voltage of 43.67 volts. So that's it. That's all it takes to calculate the new higher voltage that we're going to experience on the coldest day of the year. The hottest day temperature, the voltage is going to go the exact opposite direction because the temperature is going to be higher than 25 degrees C. And we already know that the ambient temperature from this equation is 37 degrees on the hottest day. But the ambient temperature is not the same as the cell temperature. We have an increase in cell temperature, and let's go back to this data sheet. It shows us that the normal operating cell temperature is 48 degrees. They're testing that whenever they are controlling an ambient temperature in this environment at 20 degrees C. So if the control temperature is 20 and the actual cell temperature that they're seeing under this test is 48 degrees. All modules differ slightly, but they're all pretty close to the same difference. So that's actually a 28-degree difference from the cell temperature to the ambient temperature. So as you can see with the formula that we have, we've added 28 degrees to the 37 to give us a cell temperature of 65 degrees. So we take the difference between that temperature and the standard test condition, so that's what we're multiplying, and we end up with 40 degrees C. So we plug that into our formula, multiply it by the temperature coefficient for max power, and that gives us a multiplier of 0.164. I subtract that from 1, and that way I can multiply that number by the standard test condition max power voltage. So 0.836 times 31 volts gives us 25.9. So that's it. That is our lowest voltage on the hottest day of the year, and we have our highest voltage on the coldest day of the year. Now, how do we apply this? What purpose did all that make? Why do we need to know this? Let's see. Let me go back to our other slide. And we have voltage limits at the high end, and the open circuit voltage early in the morning when our voltage is the highest, we need to make sure that we don't violate any of the voltage limits that we have. Now, as far as the National Electrical Code is concerned, 600 volts is max for residential systems. 1000 volts is maximum for commercial systems. But the equipment manufacturers also have limits as well. If it's a microinverter, they may have a limit of 48 volts. If it's a commercial string inverter, they may go up to 1000 volts. They may be going up to 900. Who knows? We have to look at the equipment that we're actually connecting up. Charge controllers, they often have a limit of somewhere around 150 to 200 to 250 volts. So that's for a battery-based system. Let's use, in our example, 600 volts. We'll consider this a residential system. And the question is, how many modules can we put in series without going over 600 volts? Well, we take the number we pulled from exercise 1 on the previous page and divide that into 600 volts. So 600 divided by 43.67 gives us 13.7. So 13 is our number. 14 would put us over 600, so we want to stay below that, so 13 is our maximum number in a string. If we were matching this up module to microinverter, we would simply look to see if this exceeds the open circuit voltage of that microinverter. And if it doesn't, then it's an approved module. Now we're looking for the minimum. These same pieces of equipment have a minimum power point tracking or minimum operating voltage before they quit working. What we want to do is stay right into the sweet spot of their maximum power point tracking range. And it varies. It depends on whether it's a microinverter, it's going to be pretty low, around 20 volts, or if it's a string inverter for residential, somewhere between 150 to 250 is the minimum power point tracking range. And a commercial inverter may have a minimum power point tracking range around 500 volts if it's a 1000 volt rated inverter. Let's use 250 as if it's a residential inverter as the minimum, and we'll take the number that we calculated from our hottest day voltage, 25.9, divided into the 250 volts, gives us 9.65. If we use 9 modules in series, we'll go below the 250, so we want to stay above that, so we round up to 10. So we end up with 10, 11, 12, 13. So we have 4 options of strings that we can put into this particular inverter. Now, if we're matching this up 1-to-1 on a microinverter, this would simply have to be higher than the minimum. So if the minimum on the microinverter was 20, then the 25.9 is acceptable and we could use that module. So that's basically it on calculating voltage for the hottest and coldest day of the year and the reason why we do it. Thanks for viewing and enjoy the day.